Okay, starting the recording. This is going to be relatively disorganized because it's not planned out. And we're starting with page 72, buffers. pH of pure water is 7. You can keep talking.
So I guess you have to do M1 V1 equals M2 V2.
Yes, because it's a dilution.
So consider 1.1 liter of water. So that's the first V1.
I would say the water, you can assume that it's basically nothing, and so the M1 and the V1 are the HCl before you dilute it. Because, like, if you think of, I guess the intuitive explanation is water, you don't dilute water. I mean, it's water. You use water to dilute other stuff.
So this here would be the V2.
By 1 and 2, let's rename them initial and final. Or which one are you talking about as your initial and which one is your final?
What are we looking for?
We're looking for...
I guess how the pH will change when that amount is added.
Right, so we're looking for the concentration of hydrogen.
So I'm saying M1 is 1.01 times this is the 1.011010. That's for the HCl.
Yes, that's the very concentrated. So I would call that the initial.
So we don't know what the molarity of what water is. So that's what we're looking for.
After mixing, yes.
They gave us the liters, which is 1.0.
Right, and really it's 1.001 because you should add them, but that doesn't matter too much.
Mm-hmm.
So, picture is you have. Is this working? Yes. So you have a beaker with water, of course, and then you put in this little bit of HCl, right? Which is much smaller than this. Good so far. I know this picture probably isn't very helpful yet, but that is what's happening, right?
Mm-hmm.
And then, so what the left side of the equation, the M1 V1, is that describing the little bit of HCl or the beaker or both?
The HCl.
The HCl. Okay, so the right side of the equation is after they're mixed, is what I'm saying. So this is all not, that's not the situation anymore. Now it's all together. The HCl is mixed in here. And that, what is that volume? It was 1 liter, but now it's they're mixed together.
Oh, okay, got it.
And she might not have written that because this is an insignificant addition. It's 1.001, which basically it's approximately 1.
So I got 1.001, which is 1.
Because sig figs. what 1 point. This one's 2 sig figs, or 1 decimal place really because it's added. Basically, such a small addition, you don't even care. But it's good to be aware of what we're actually doing. Even though it doesn't.
yeah. I was going to take this though and say it was that, which is what it is. It's that.
And I'm saying it is that. It's both combined, but for practical purposes.
So I'm going to take this here and divide by that.
Yeah. And here, the reason I'm insisting on being precise is because she could have made it a different example where it's 1 liter of water and 1 liter of HCl. And then, yeah, it really matters that the final... I'm going to write that out. First, I'm going to write what you're saying.
M2 equals 1.00. So that would be the molarity of the water.
Yes. The molarity of what? The concentration of what?
The water in HCl.
Molarity always means moles per liter.
Mole per liter, yeah.
Moles of what? Since this is a concentration, it's a molarity. It's moles per liter. So moles of,
I don't know,
HCl per liters of
water.
everything. Liters of whatever.
Okay.
Liters of solution. So why do we care about the moles of HCl? Why do we care about the moles of H plus is actually the question. Because that's how you find pH. pH equals log H plus.
And that's same as H3O plus.
Yes.
So you'll take this.
Oops. Okay. In this case, H plus is the same thing as the concentration of HCl. Why is that? Because it's a strong acid, so all of it splits.
Oh yeah, it is strong acid.
So we didn't have to do any fancy ice table stuff. It's just all of it splits up.
Yeah.
We can find the H plus.
3.
So, is that a big change from 7?
Yes.
And that's what she's trying to point out. Stuff's not well buffered if you don't buffer it yourself.
Okay. I got that. Okay.
The second example with the delta pH of NaOH is exactly identical, so I'm not going to show it. The one difference between the last problem and this example is that you end up finding pOH to be 3, just as we found pH to be 3 on the previous, and so you have to do this 14 minus to find pH, which gives you 11, as we know from class.
I don't understand.
The delta pH, it starts at 7 because it's water, it's neutral.
Okay.
She just said, hey, look at how big of a change it is. 4. That's an enormous change on the pH scale. And so we're going to show with buffers that it doesn't change that much. It's going to change by like 0.2 instead of 4. So that living beings don't die. That's why blood is a buffer.
Got it. buffer against a base? No.
Right.
Okay. And what would you need in there for water to be, well, add a base to neutralize it? What might you need? What would you need, a base?
Well, if you're adding base, you would want acid in there, and if you're adding acid, you would want base in there. So somehow you have to have both in there, and that's what buffers are, having both.
A mixture of acid and a base.
Yes, and you pick the right ones so that they don't cancel each other out. Because you might at first think, oh, if I just mix acid and base together, it'll just cancel each other out, and we're back where we started. That's not what happens if you pick the right stuff.
So you have to have a strong acid and a...
Not a strong acid. Right there at the bottom of page 72. The most effective buffers are composed of a weak acid conjugate base pair or a weak base conjugate acid pair. Strong ones won't buffer at all.
Okay, got it. Let me just write the reaction for equalization here.
Consider a solution containing 0.2 molar HF and 0.2 molar NaF.
So you got HF, right?
Yes. So we're just writing it. Not plus each other like that. It's more like since you have if on the next page, page 73, we do an ice table, and that actually shows what the effect is. But basically, the idea is you have this reaction, HF. Definitely not going to go on the screen, so I'm going to do it over here. So, not that. HF plus water. Goes to F minus plus H3 plus. So with this reaction,